Here's the narration. You're given a string of ones and zeros, where a 1 means an active section and a 0 means an inactive one. You're allowed to do at most one trade. First, you take a solid run of ones that has zeros on both sides and flip it all to zeros. And then you take a solid run of zeros that has ones on both sides and flip it all to ones. Your goal is to return the largest number of active sections you can end up with.
Green circle beginner level. Here's something that sounds backwards. We're going to erase some ones and somehow finish with even more ones than we started with. It really works, and by the end of this video, you'll be able to see the trick right away. Take your time. There's no rush. It all comes down to a single number, and I'll show you exactly which one. You might wonder where this ever comes up. It shows up anytime a computer tries to tidy up scattered pieces of storage and pack them together, like when your computer defragments a disk to clean up the mess. Big companies like Google and Meta ask about it in interviews because it looks hard but really just hides a simple counting idea. Learn that idea once, and lots of similar problems suddenly feel easy. We're given a string made of only ones and zeros. Think of a 1 as on and a 0 as off. You get exactly one move. First, pick a group of ones that has zeros on both sides and turn them all into zeros. Then pick a group of zeros that has ones on both sides and turn them all into ones. One small note. We imagine a 1 stuck onto each end of the string, so even the pieces at the very edges have something next to them. Our goal is to end with as many ones as possible. Let's slow down and try a small one together. Start with 0-1-0-0. Now stick a 1 on each end, giving us 1-0-1-0-0-1. Look at that single 1 in the middle. It has zeros on both sides, so we're allowed to turn it into a 0. Now all the zeros between the two outer ones sit together as one big group. We fill that whole group with ones, and the original part now reads 1-1-1-1. That's 4 ones. See, it really happened. There are only 2 little ideas to hold on to. The first is just grouping the string into chunks where the same digit repeats. So instead of writing 3 zeros and then 2 ones one by one, we say a group of 3 zeros, then a group of 2 ones. People call each chunk a run, but it just means a group of the same digit. The second idea is simply counting how many ones we have at the start. That's our starting score before we make any move. Here's the heart of it, and I like to call it the zero bridge. Picture a group of ones with a group of zeros on its left and a group of zeros on its right. When we erase that group of ones, it's like removing a wall, so the zeros on the left and the zeros on the right join into one big group of zeros. Then we fill that whole thing with ones. So the ones we just removed come right back as ones, and on top of that, every single 0 on both sides also becomes a 1. That's the free bonus.
Now everything comes together. Your final score equals the number of ones you started with, plus the biggest total of left zeros plus right zeros you can find around any single group of ones. The group of ones you erase comes right back, so it doesn't add or subtract anything, which is why it never shows up in the math. And remember that mystery number I promised at the very start? This is it. It was just the left zeros plus the right zeros all along.
Let's walk through the code slowly. First, we stick a 1 on each end, so every real group has neighbors on both sides. Then we count our starting ones and remember that number. The loop then walks through the string 1 time from left to right. Each time, it slides forward as long as the digit stays the same, which neatly cuts out one group. We save each group as 2 things, which digit it is and how long it is. That's all this part does. Now we look for the best bridge. We skip the very first and very last groups because a bridge needs zeros on both sides, and those 2 edge groups are the extra ones we glued on, so they can't count. For every group of ones that has a group of zeros on each side, we add up the sizes of those 2 zero groups, and we keep the biggest total we find. At the end, the answer is simply our starting ones plus that best total. Nice and short. Time for a little challenge, so go ahead and pause the video. Our string is 100100. Count the ones, and you get 2 to start. Now find the group of ones that has zeros on both sides. Add up the 2 zero groups next to it, and try to work out the final answer before I reveal it. There's no pressure, just give it a shot. Let's check it together. That middle group of ones has 3 zeros on its left and 2 zeros on its right. So the bridge gives us 3 plus 2, which is 5. Add that to our 2 starting ones, and we get 7, the whole string turned on. If you got 7, wonderful, the 0 bridge is already clicking for you. And if you didn't, that's totally okay. Just walk it through once more. Now, your first instinct might be to actually try every possible move. Make the trade, rebuild the whole string, count the ones, and repeat. And you know what? That does give the right answer, and it feels safe on small examples. The trouble is that on a really long string, say 100,000 characters, you end up rebuilding the whole thing thousands of times, and it becomes painfully slow. I'll be honest, the first time I saw this problem, I wrote exactly that, and it was too slow to finish in time. Let's talk speed in plain terms. And just means how long the string is. The try everything way is slow because each move touches the whole string, so the work grows roughly like n times n, which gets huge fast. The 0 bridge reads the string just twice, once to make the groups and once to scan them, so its work grows only in step with n, which is much friendlier. Both use about the same amount of memory. My honest take, the slow way isn't even worth writing, because the group version is barely more code and enormously faster. Let's make sure the weird cases don't break us. If no group of ones has zeros on both sides, then best just stays 0 and we return our original count, which is exactly right. If the string is all zeros, there are number ones to fill anything with. And if it's all ones, there's nothing to trade, and both of those work out fine on their own. And those 2 extra ones we glued onto the ends, they're what keep the edges from causing errors when we check the neighbors. Remember how we opened with deleting ones to somehow get more ones? Now you know why. Erasing a group of ones joins the zeros on both sides, and we flood that whole gap with ones. So the recipe is group the string into runs, count your starting ones, find the fattest pair of 0 groups around a single group of ones, and add them up. That's the whole thing. You did great sticking with it. A new problem drops tomorrow at the same time, where this same grouping trick cracks a trickier one. Off by 1 mistakes are sneaky, but that subscribe button is easy to find. It's right there. Yellow circle intermediate level. You delete blocks of ones and end up with more ones. How? By the end of this, you'll spot the winning move in seconds, I promise. Stick with me, because one single number does all the heavy lifting here. This exact shape shows up whenever you compact fragmented space. Think defragmenting a disk or squeezing memory blocks together. Companies like Google and Meta love it because it hides a simple counting trick behind a scary-sounding trade. Learn the trick once, and a whole family of run-based problems opens up. You get a binary string. In one trade, you take a block of ones that has zeros on both sides and wipe it to zeros. Then you take a block of zeros that has ones on both sides and light it all up. We pretend the string has a 1 glued to each end, so even the edges have neighbors. Take 0, 1, 0, 0 and glue ones on the ends to get 1, 0, 1, 0, 0, 1. That lonely middle one has zeros on both sides, so we erase it, and now all the zeros between the outer ones form one big block. Fill that block, and the original part reads 1, 1, 1, 1. For active sections, only 2 ideas today. A run length encoding just means grouping the string into chunks of the same bit, like saying 3 zeros, then 2 ones instead of spelling each out. In a plain count of ones, our starting score before any trade. Here's the trick, and I call it the 0 bridge. When a run of ones sits between 2 runs of zeros, deleting that one run drops a bridge, so the left zeros and right zeros become one giant 0 block, which we then flood with ones. So the ones we destroyed come straight back, plus every 0 on both sides turns to 1 for free.
Now the moment it all clicks. Final score equals your original count of ones, plus the biggest left plus right zeros you can find around any single one run. The one run you erase cancels itself, so it never even appears in the math. That mystery number I teased at the start, it was Z1 plus Z2 all along.
First, I glue the guard ones on so every real run has neighbors. Then I lock in my starting count of ones. The while loop walks the string once, and each time it slides, K forward while the bit stays the same, so it snips out one clean run at a time. We store each run as its bit, and its length.
I skipped the very first and last runs because a bridge needs zeros on both sides, and the guards break that. For every one run sandwiched by zeros, I add its 2 zero neighbors and keep the largest total I've seen. Then the answer is just my starting ones plus that best bridge. Clean.
Quick challenge, pause the video. The string is 1000100, which has 2 ones to start. Find the one run with zeros on both sides. Add those 2 zero groups, and tell me the final answer before I show it. That middle one run has 3 zeros on its left and 2 on its right, so the bridge gain is 5. Add it to our 2 starting ones, and you land on 7, the whole string lit up. If you got 7, the zero bridge already lives in your head. The brute force instinct is to actually perform every possible trade, rebuild the string, and count. It works, and it feels safe on the examples. But on a string of 100,000 characters, you're rebuilding the whole thing thousands of times, and it crawls. Honest confession, the first time I hit this, I coded exactly that simulation and watched it time out. The simulation is big O of n squared because every trade touches the whole string. The zero bridge reads the string, wants to build runs, and wants to scan them. So it's plain big O of n time and big O of n space. My honest take. The simulation isn't worth writing even as a warm-up. The run version is barely more code and infinitely faster. If no one run has zeros on both sides, best stays 0, and we just return the original count, which is exactly example 1. All zeros gives no ones to fill, and all ones gives nothing to trade, and both fall out correctly. The guard ones we glued on are what stopped the ends from crashing the neighbor check. Remember the cold open, where deleting one somehow made more ones. Now you see why. Erasing the one-run bridges, it's 2 zero neighbors, and you flood the whole gap. Group into runs, add the ones, find the fattest zero pair around a single one run, done. New daily drops tomorrow, same time, where this same run length trick cracks a nastier compression problem. Off by 1 bugs are sneaky. The subscribe button is not. It's right there. Red circle advanced level. You know this shape. A merge problem wearing a deletion costume. Erasing a one-run bridges its 0 neighbors, so you recoup the ones and pocket the gap. Real question isn't how it works, it's whether you could defend the O, in, reduction, and the guard trick under interview pressure. Let's stress it. The interesting follow-up isn't the discompaction framing. It's what happens when the operation generalizes. Multiple trades, weighted runs, or a streaming variant where you can't hold the full string. Each of those changes whether run length, plus a single scan still buys you optimality. Keep that in your pocket for the now what if turn. 1 trade. Nuke a bounded 1 run, then flood a bounded 0 run. The subtlety everyone understates is that both operations must be bounded on both sides, which is exactly why the fan and guard ones on the ends matter. Skip the guards and your boundary runs silently become ineligible or eligible incorrectly. That's the whole ball game. 0-100 augmented to 1-0-1-0-0-1. The point of this trace isn't the arithmetic. It's confirming the guards make the interior 1 eligible when it otherwise sits against a string edge. Notice the guards never enter the count. They're pure sentinels. If you've ever done sentinel nodes and linked list problems, same instinct applied to runs. Run length, encoding, plus a base count of ones. Worth noting you don't actually need to materialize the runs list. You can carry a rolling window of prevo len, cur1 len, nextvo len, and stay O1 space, dropping from O to O1 auxiliary. We build the list here for clarity, but flag that micro-opt if space is the constraint they're probing. The bridge, a 1 run flanked by zeros. Erase it. The 2 zero runs coalesce, and you flood the union. The reason the 1 run's length is irrelevant is the exchange argument. You destroy K1s and refill K in the merged gap. Net 0 on the ones you touched. That cancellation is the invariant you'd prove if asked why greedy on max neighbor sum is optimal.
Answer equals total underscore ones plus max over eligible 1 runs of Z1 plus Z2. The erased run cancels, so run length never appears, which also means ties and run length don't matter and you're purely maximizing a neighbor pair's sum. If they push on optimality, any single trade only ever merges two adjacent zero runs, so the global optimum is just the best local merge. One pass suffices.
Guards concatenated, base count taken before augmentation so the sentinels don't pollute it. The two-pointer run builder is the standard linear group by. K races ahead while the bit holds. Nothing exotic, but note ones is computed on S, not T. That ordering is load-bearing. If you wanted the O, 1, space variant, this is the loop you'd fuse with the scan below. Interior-only scan, range 1 drops the guard runs so the boundary neighbor checks never index out. Because RLE alternates bits, the 0 on both sides test is technically redundant for a 1 run, but it's cheap insurance and reads as intent. Best defaults to 0, which is exactly what makes the no-eligible run case return the untouched count for free. 100, 0100, 2 ones. Don't count by hand. Do it the way the code does. Find a single interior 1 run, sum its flanking 0 lengths, add to base. If you can name the answer before the reveal, you've internalized the reduction, not just the story. Middle 1 run flanked by 000 and 00, gain 5, plus base 2 equals 7, full saturation. Sanity check the upper bound. 7 is lens. So this input is a case where a single trade fills the entire string, which only happens when there's exactly one interior 1 run. Useful edge to have named. The naive baseline simulates each trade and rebuilds O, N, per trade over O, N. Candidate runs, so O, N squared, with a fat constant from string reallocation. Worth stating out loud in interview, even though you won't code it, because contrasting it is how you justify the RLE reduction. Then immediately abandon it. Brute force O, N squared time. 0 bridge O, N, time, and O, N. Space as written only because we store runs. Collapse the 2 loops into 1 rolling window, and you're at O, 1 auxiliary. That's the micro-op to reach for if they cap memory. And it's the honest answer to can you do better on space. The traps. No interior 1 run returns base untouched via best equals 0. All zeros. Base is 0. No eligible run, return 0. All ones, single run, nothing to trade, base returned. Empty string, guards make T equals 11, 1 run, still safe. And a 1 run touching an original end. That's the exact case the guards rescue. Without them, your neighbor lookup either faults or wrongly rejects. That's your whole edge case matrix. Reduction in 1 line. Base ones plus the max adjacent 0 pair around any interior 1 run. Guards handle boundaries. Exchange argument handles optimality. Rolling window handle space. That's everything you need to reconstruct it cold or extend it to the K-trades variant, which is where tomorrow's harder RLE problem picks up. Off by 1 on the guard bounds is the one bug that bites here, so watch the range. Subscribe. It's the only trade with no downside. First one. If the string is already all ones, what's the answer? Pause and take a guess. Think about what the trade actually needs to work. It's unchanged, the total ones. With no zeros between groups, there's nothing to merge, so you gain nothing. Second question. When you pick a 0 group to bridge, how many groups of ones get combined? Pause and think. Remember what sits on each side of that 0 group. 2. The ones just left and just right of that 0 group. Sliding it away lets those 2 touch and merge into 1.